We are going to look at a question of how we would predict a rate law from a reaction mechanism in which the rate determining step, or the slow step, is not the first step. Rather, as you can see here, it is the second step. So let's start, before we do that, by figuring out what our overall chemical reaction is. Our overall chemical reaction we can determine by canceling things that appear on both sides and then adding up our total reactants and adding up our total products. So we see here that there are 2 chlorines on the right side, and there are 2 chlorines also on the left side, and those will cancel. We can also see that there is a CCl3 carbon trichloride on the right side and on the left side. Those will also cancel. So that is going to leave then, for our overall reaction, a diatomic chlorine, Cl2, and this CHC, oops, CHCl3, this trichloromethane, and they will react to form a HCl and a CCl4, or carbon tetrachloride. That is going to be our overall reaction. Now, let's look at these products that canceled. You notice that these, if we look at our 2 chlorines, they are produced in the first step, and then they are used up in the second and third step. Or my CCl3 is produced in the second step and used up in the third step of the mechanism. These are going to be intermediates. Intermediates are compounds or elements that do not appear in the overall reaction. You notice none of them are in this overall reaction. But they are produced in earlier elementary steps and used up in later elementary steps. So my intermediates are going to be chlorine and the CCl3, okay? Notice there are 2 chlorines here, but that just means it's a 2-to-1 mole ratio. It is not going to be a compound called 2Cl. There's no such compound as called 2Cl. That coefficient of 2 is just a mole ratio. So the intermediates are going to be these species right here. Now we can predict a rate law for the reaction. And a rate law is predicted from the rate law of the slow elementary steps. So we can start by writing the rate law. And the rate law of the overall reaction is going to be equal to the rate law of the slow, or rate determining, elementary step. So in this case, that would be step 2. So to write that rate law, the rate law of that elementary step is going to be equal to the rate constant K times my chlorine, and there's a coefficient of 1 here, so it would be to the first power, which is unwritten, and then also the CHCl3. So that is the rate law of elementary step 2, and it should be the rate law of the entire reaction. But we have one problem here. The problem is that an intermediate cannot appear in the rate law. Only species in the overall reaction can appear in the rate law. So the overall rate law must be of the form of K Cl2 to some power. We don't know what it is, so we'll call it A. And my other reactant, CHCl3, and that is to another power, B. So this is what must appear in my overall rate law. Now, they don't both have to appear. One of these could be a 0 power, for example, and not be there. But the point is, this intermediate cannot appear in the rate law. So what we have to do next is that we have to get rid of the intermediate. We must eliminate our intermediate. And the way we can eliminate that intermediate is by substitution. Okay. Now, if we look at our first reaction, we see that it is an equilibrium reaction. And generally, any steps going before the slow step will be an equilibrium. Okay, here's why. Even if it's not a true equilibrium, we can approximate it as an equilibrium. And the reason for that is this first reaction goes very fast and this second reaction goes very slow. So what's going to happen is we're going to get a bottleneck, or the reaction is going to kind of get stuck right here while it's waiting for that slow second step. So we're going to get a buildup of this chlorine product from my first elementary step. So even if it's not a true equilibrium, we can approximate it as one. So if we look at an equilibrium, I'm going to rewrite my equilibrium down here, and that is Cl2 in equilibrium with 2Cl, which is my step one. And since that is an equilibrium, the rate of this forward reaction is going to be equal to the rate of the reverse reaction. The rate of the forward is going to equal the rate of the reverse. That's the definition of equilibrium. Now, if I were to write a rate law of the forward reaction, that's going to be K, and I'm going to call it K forward, Cl2. And that's a 1, so that would be to the first power. The reverse rate would be going in this direction, so that's going to be KR. I'll call it KR for K reverse, and that's going to be Cl squared. Coefficient of 2 gives me a second power. Now, I want to eliminate this Cl. So what I'm going to do is I'm going to solve this equation for Cl. The way I can do that is I can divide both sides of this equation by Kr. That will allow me to cancel these K reverses, right? And then I'm going to take the square root of both sides. And if I take the square root of both sides of this equation, I will get Cl. and that will essentially be the square root of all of this. And another way to write the square root is the 1/2 power. So that would be Kf over Kr times Cl2 to the 1/2 power. That is what my Cl is going to equal. So now I can take this and I can substitute it back in here for my overall rate law. So my new rate law is going to be Kf over Kr, and that is to the 1/2 power, times my Cl2 to the 1/2 power, and that is going to equal, excuse me, that's it, not Cl. Not equal Cl, but my CHCl3 from up here. So again, this replaced my Cl in the rate law. Now I can clean this up a little bit. All of these constants can be grouped together. A constant times the forward constant to the 1/2 power divided by the reverse constant to the 1/2 power is just going to be a constant. So I'll still call it K. And then I'm going to have a Cl2 to the 1/2 power times CHCl3. If we notice, these are both reactions in my overall reaction. My species in my overall reaction is diatomic chlorine and the CHCl3. That's what I have down here. My intermediate has been eliminated, so this is my overall predicted rate law.